Hello good people, I'm going to talk about autoionization of water. It involves a transfer of a proton from one water molecule to another. In other words, water can act as both an acid and a base. It is said to be amphoteric. In terms of a chemical reaction equation, we could say that the green water molecule will react with the purple water molecule to give a hydroxide ion and a hydronium ion. And in terms of Lewis dot structures, we would have something like this. The purple water molecule would act as a base, whereas the green water molecule would act as the acid. Using the Bronsted-Lowry model, I could say that the green water molecule is going to donate one of its protons to the purple water molecule. And in terms of a Lewis acid-base definition, I could say that a lone pair of electrons on the oxygen of the purple water molecule will be donated to one of the hydrogens on the green water molecule. At the same time, the two electrons that make up the bond between the oxygen and the hydrogen on the green water molecule will end up with the oxygen. And so when all is said and done, the products would be a hydroxide ion and a hydronium ion. Water has reacted with itself to give two ions. This is why this is called autoionization of water. Note again that this is an acid-base reaction. The green water molecule was the acid and it gave the conjugate base of the hydroxide ion. The purple water molecule was the base and it gave the conjugate acid of the hydronium ion. This autoionization reaction can be simplified, and we could say that water dissociates to give a hydrogen ion and a hydroxide ion. But, and this is very important, it does not dissociate completely. That is to say, not all water molecules will be split into hydrogen and hydroxide ions. And I can already hear you asking, well, how many will split into hydrogen and hydroxide ions? The answer is not very many. In fact, only 1 in about 555 million of water molecules will undergo this autoionization. What is more, the autoionization is temperature dependent. In pure water at 25 degrees Celsius, the concentration of hydrogen ions is same as the concentration of the hydroxide ions. And that concentration happens to be very, very small. Only 1 × 10⁻⁷ moles per liter. Although this number is very small, it is very important. When we multiply the concentration of hydrogen ions by the concentration of hydroxide ions, the product that we end up with is the water dissociation constant, also known as Kw. Mathematically, this would be expressed as 1 × 10⁻⁷ multiplied by 1 × 10⁻⁷, which equals 1 × 10⁻14. Once again, we have ended up with a very small number, but it is an important number. We will explore this later some more. For now, it is important to recognize the meaning of this Kw. In any aqueous solution at 25 degrees Celsius, no matter what it contains, the product of the concentrations of hydrogen ions and hydroxide ions must always equal 1 × 10⁻14. This means that we have 3 possible scenarios. The first one is that we have a neutral solution. In that case, the concentration of hydrogen ions has to equal the concentration of hydroxide ions. If the concentration of the hydrogen ions is greater than the concentration of hydroxide ions, we are dealing with an acidic solution. And conversely, if the hydroxide ions concentration is greater than the hydrogen ion concentration, we are dealing with a basic solution. At this stage, you might be thinking that not only are these numbers tiny, but they are also a bit awkward. That is correct. And that is why in chemistry and other sciences, when it comes to measuring the acidity of a solution, we rely on the pH scale. But more on that later. That is all for now, and I will see you on the flip side.